Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I am so grateful for the opportunity given by IAGI committee to deliver my current work in geochemistry. My name is Ario Budi Wicaksono. I work as geochemist at the Exploration Division of Research and Development Center for Oil and Gas Technology, LEMIGAS. The title of my presentation is Detection and Utilization of Diamondoid Hydrocarbon in a Condensate Sample from Eastern Indonesia. The rundown of my presentation is, first, introduction, to give a brief knowledge about diamondoid, how it's generated, and how we can use it in petroleum exploration. Second, background, about why this topic is selected. Third, method. Method will tell how I perform analysis in the laboratory. Fourth, result and discussion. We'll show result of laboratory analysis, how to process the data, and what kind of interpretation can be made. And last is summary, to give the result of this research and what is the future plan. What is diamondoid? This is adamantan, a symmetrical structure composed by 3 rigid fused cyclohexane rings in chair configuration. Adamantan is the simplest representative of diamondoid hydrocarbon. Adamantan was isolated first time in 1933 from petroleum in Czechoslovakia. This molecule was named adamantan based on a Greek word adamak, a noun word for diamond. The polyhomologues of adamantan include diamantan, triamantan, tetramantan, pentamantan, and hexamantan. Diamantan, triamantan, and their alkyl substitute compounds are also present in certain petroleum crude oils. Tetramantan, pentamantan, hexamantan were discovered for the first time in 1995 in a condensate produced from the Gulf of Mexico. Ford and von Sleyeren in 1964 suggested that adamantan could have been formed during petroleum genesis from cyclic hydrocarbon precursor by Lewis acid catalyzed isomerization and rearrangement through a mechanism similar to that observed during the synthesis of adamantan from endo-3-cyclodecane. Diamondoid do not occur in organisms and structurally very different from their probable precursor in living organisms. Why I choose this topic, the diamondoid? In geochemical analysis of petroleum, commonly we use the ratio of alkanes and acyclic isoprenoid, steren, diasteren, terpenes, and aromatic steroid. These compounds are biological markers, which are compounds derived from living organisms. For example, steren is derived from sterol found in higher plant and algae. Triterpene is from terpenoid found in bacteria. Likewise, with specific biomarker such as batriococan derived from Botryococcus browni and bicadinine derived from damarcin. All of these biomarkers are used to interpret the source input, the positional environment, and also the level of maturity. However, they are prone to affected by various processes, including biodegradation, evaporation, and oxidation. As a government research institution, LEMIGAS conducted geological fieldwork and discovered several oil seepage. This picture is the oil seepage found in Malacca region, West Timor. This oil seep was found when the sea level is falling. The oil is biodegraded, although some biomarkers still recognizable because the oil is freshly coming out along with the gas. But we are not always lucky to have such kind of oil seepage. Sometimes the level of biodegradation is so severe that most biomarker disappears. In several occasions, Our laboratory also received sample from oil spill case. This is the picture of oil spill case in Bintan Island. Previously, we have a database of oils in Indonesian producing basin from Aceh to Papua. So when the fingerprint of this spilled oil match in our database, then we can trace from where the oil is sourced from. But unfortunately, due to the various processes, including evaporation and biodegradation, most of the biomarker in the oil spill already removed. We need alternative solution to trace source of oil spill and also to gain information from seepage for exploration purposes. Through literature study, it is known that diamondoid hydrocarbon are more stable and resistant to biological degradation. Therefore, the ratio of diamondoid hydrocarbon might be used to solve geochemical problem when commonly used biomarkers are not available. Several samples from various conditions and location were planned to analyze, including oil seep and oil spill. However, due to limitation of access to laboratory caused by the COVID-19 pandemic, the only sample was able to analyze is the condensate sample. The analysis of diamondoid is similar with routine oil fingerprint analysis. Diamondoid occurs in saturated fraction of petroleum, which can be separated from oil using liquid chromatography method. In this work, the condensate sample was directly injected into GCMS without the further sample workup. GCMS analysis of condensate sample was performed using an Agilent 6890 gas chromatograph coupled to an Agilent 5973 series mass selective detector in full scan mode. The GC was fitted with 60 meter, 0.25 millimeter inner diameter DB5MS fused silica capillary column. Sample was injected using an Agilent 7673 auto sampler with split ratio 1:350. The GC oven was programmed from 50 degrees Celsius, held for 5 minutes, and rise to 80 degrees Celsius at 15 degrees Celsius per minute, then rise again to 200 degrees Celsius at 2.5 degrees Celsius per minute, and finally to 300 degrees Celsius at 15 degrees Celsius per minute, and held for 10 minutes. Helium was used as the carrier gas at a constant flow rate of 1.5 milliliter per minute. The chromatogram of GCMS saw very good result. The normal alkan in MC57 saw domination in lighter hydrocarbon compounds peak at C11. The adamantan and their alkyl side chains can be observed through MZ 135, 136, 149, 163, and 177. The abundance of adamantan compounds is much higher than their diamantan counterpart. The diamantan and their alkyl side chains can be observed through MZ 187, 188, 201, and 215. The identification of individual adamantans and diamantans compounds was determined based on a comparison to previously published relative retention time and full scan mass spectra, for example, from Stott and Douglas, 2004. Using the ratio of adamantan, diamantan, and their methyl and ethyl group, we can interpret the level of maturity, level of biodegradation, source input, and depositional environment of oil. To interpret the level of maturation, methyl adamantan index is used by the ratio of width area of 1 methyl adamantan to 1 methyl adamantan plus 2 methyl adamantan obtained from MZ135. The next ratio is methyl diamantan index, which is the ratio of 4 methyl diamantan the summary of 1-methyl diamantan, 3-methyl diamantan, and 4-methyl diamantan obtained from MZ187. Both ratios are presented in percentage. These ratios are based on the research by Chen et al. In 1996, who observed the increasing of this ratio with the increasing of vitrinite reflectant in source rock and oil in several basins in China. The result of the ratios are the methyl adamantan index is 78% and methyl diamantan index is 48%. As comparison, ratio of aromatic biomarker commonly used to determine the level of maturity, which is methylphenanthrene index, is also calculated with result is 1.17. The methyl adamantan index and methyl diamantan index are equivalent to vitrinite reflectance value between 1.3% and 1.6%. Meanwhile, calculated vitrinite reflectance value using the methylphenanthrene index by formula of Radke and Welte is 1.6%. Therefore, based on diamondoid ratio and aromatic biomarker, both have an agreement that the condensate is on overmature stage. To assess the biodegradation level, we can use the ratio of methyl adamantan to adamantan taken from MZ135 and 136 respectively. The ratio of methyl adamantan to adamantan is 6.85. Clitigris and her colleagues in 2000 have been investigated the effect of biodegradation on diamondoid distribution in petroleum reservoir in Australian basin. Their research shows that the ratio of methyl adamantan to adamantan rises with the increasing biodegradation. The value is 5.3 for non-biodegraded oil and 15.1 for very severe biodegraded oil. The ratio of methyl adamantan to adamantan value of 6.85 in this sample is close to methyl adamantan to diamantan ratio of slightly biodegraded oil. This is also shown by the depletion of low carbon numbered alkane. Relative abundance of dimethyl diamantan compounds have been used by Schulz et al. In 2001 to distinguish between terrigenous, marine carbonate, and marine silicic clastic source rock from various locations in Europe, because these compounds are virtually unaffected by maturity. Using a ternary diagram, the relative distribution of dimethyl diamantan obtained from MZ to 101 can be seen in this graph. And the condensate sample in this research is close to the group of type 2 carbonate rock. The ethyl adamantan ratio can be used to distinguish different phases. However, it is limited to oil window maturity, make it not applicable to high maturity sample such as condensate in this research. However, Anlaima in 2006 combines the ethyl adamantan ratio with dimethyl diamantan ratio to distinguish lacustrine and marine oil from Tarim Basin in China. If we plot our sample in the diagram, then the condensate sample is classified as marine oil. As summary, this work successfully proved that the maturity level of condensate sample is in an overmature stage aided by the ratio of methyl adamantan index, methyl diamantan index, or by the calculation of methylphenanthrene index. The decreases in concentration of lighter hydrocarbon indicates the condensate is slightly biodegraded and confirmed by the ratio of methyl adamantan to adamantan. Ethyl adamantan and dimethyl diamantan ratio shows that the condensate sample is marine oil sourced from type 2 carbonate rock facies. Analysis and interpretation only on one sample, of course not sufficient to draw a complete conclusion on how diamondoid might be used as an alternative in geochemical interpretation of hydrocarbon. Therefore, for the future plan is to analyze diamondoid on more type of samples as arranged previously to have complete range on how we can use diamondoid in various conditions of oils. Analysis will perform using the selective ion monitoring rather than the full scan mode in GCMS, and analyzes the sample in not in whole oil but in saturated fraction to achieve higher resolution dataset. I would like to acknowledge management of LEMIGAS for supporting this work. Special thanks to Ms. Desian Susnimar, Ms. Fitri Yuliani, and Mr. Dwi Suryanto of LEMIGAS Geochemistry Group for their assistance in laboratory analysis. This is the end of my presentation. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.